them. And I am extremely lucky to have such talented students in my group. And I would like to thank them all as well. Right. The content of this talk will be a little bit on history of graphene and then common graphene fabrications that are currently employed. And after that, we will talk about what laser scribe graphene is, how it is made, and how we make it. And after that, we'll share some characterization results as well as prospective applications. Graphene is, with the most basic definition, it's an allotrope of the carbon. It consists of a single layer carbon atoms that are connected through a hexagonal honeycomb structure planet. The ideal form is one layer, but you don't really have it in one layer. Okay? To be frank, most of the fabrication techniques will give you a few layers, okay? Or they will give you a foamy type fluid. One can give you a single layer, which is CVD, chemical vapor deposition, but even CVD will give you a few layers when sort of characterized thoroughly. So single layer graphene is still a little bit far away. People get it, that's fine. But if you imagine on an industrial level, you imagine a 10 to 10 centimeter, which is the standard for microelectronics, nanoelectronics, we call it, vapor size. If you make 10 to 10 with CVD, you will get single layer at some places, but definitely will get a few layers at other places. So it usually comes to you in a, let's say, hybrid thickness. The first, so it was actually discovered theoretically in 1940s, but after that, Game and Novoselov, they could obtain a few layers of graphene by mechanical exfoliation, which was simply taking a graphite powder and applying scotchy tape on it constantly to reach a few layers. That discovery, however, led them to win Nobel Prize in 2010. And after that, it was a gold rush. Okay, graphene was complete gold rush. Before 2010, people were all into CNTs, carbon nanotubes, which is the rolled form of graphene. Okay? But after 2010, everyone was like, oh yeah, that's the holy grail. We are all gonna get into graphene. That is why it has been used a very wide range of applications. You can see graphene-based biosensors, field effect transistors, solar cells, anything you name it has been done by graphene, or at least in research field, people try to do it. Some were succeeded to industrial level or scaled up versions, some, but most. Okay. If you look at main fabrication techniques, the first is micromechanical exfoliation, which is simply mechanically grinding graphite into smaller pieces. And the second one is liquid phase exfoliation that involves either chemical or electrochemical substance sort of processes to break down graphite into single layer graphenes. The third one is chemical vapor deposition, and the other one is flame synthesis, or flame pyrolysis, which is similar to making CNT, but with a little bit different type of catalysts, pulse laser deposition, and then lastly, well, not least, laser induced or scribe deposition that we are going to talk today. So laser-induced fabrication is the most common one. It was introduced around 2040 by two different research groups. And the idea of laser scribing is every material, almost every material, has a tendency to absorb the light, and laser is a light. The idea here is introducing laser with a high energy density on a surface. When material absorbs that energy, it breaks down all the bonds, okay? Especially if this is a polymer film or any type of organic film. It absorbs the energy, and hence the bonds of functional groups are broken. That's what it does. And remaining atoms, remaining carbon atoms, regain themselves together to form the most stable version, which is hexagonal graphene bond. So that's the whole idea. The trick is though, each material has different models, whether they are polymers. For instance, polymer can be converted by a carbon dioxide. Whereas PDMS, which is another polymer, it's an elastomer. You cannot convert PDMS with carbon dioxide because it doesn't absorb it. Instead, it absorbs diode lasers, which has a different wavelength. Okay? Or if you want to convert graphene oxide to graphene with laser, then you have to use EVD writer laser. Because that material is self-absorbed. That kind of thing. Okay, so this is all if you have a polymer film, or if you have any type of organ, it could be even a fluid, okay, a surface of the fluid. You just have to check different types of laser to make sure that it absorbs it correctly. Okay? In our case, we will have a carbon dioxide laser, and we work with polyamide films. The beauty of our laser is that it is extremely cheap. Okay. The counterparts used in literature, they cost more than 20,000 USD. Okay. But we got this laser for 500 USD. So it's very cheap, and it is exactly the same. Okay. We do have our laser. If you look at the components of laser, you see we do have a laser. Inside and outside the laser has sort of optics, and those optics can laser to the laser. They go on the surface of the laser head, and micro stages allows. Okay, so this one. Right, so the micro stages allows movement of laser head to X and Y axis, which then gives you sort of permission to draw any pattern that you want. Okay, so you can create patterns during the fabrication, and that is an extremely big advantage. Usually, you fabricate first, and then you prefire it, and then you transfer it, and then you pattern it. This system does everything in one step. All right. And in terms of how it works, we do have our polyamide thing, and polyamide is usually in color of amber or dark yellow. And we apply laser lighting to software that in which we can adjust the laser, we can adjust the parameters such as laser power, scanning speed, and resolution. And after that, with the selection and you can select your pattern, or you can draw your pattern through that software as well. And what happens is you get graphene only the exact parts that you pattern, and the rest remain untouched or unharmed. There are two important parameters for laser scribe graphene fabrication. One is the power, obviously, the power of the laser. In our case, we use a 50-watt carbon dioxide laser, and we do apply 10 to 25, between 10 to 25 volt ranges to see where we can get the graphene. And it turns out we get a good conversion when we apply 18 plus minus 2% of 50-watt laser with a speed of 375 millimeter per second with 1,000 dpi setting. We can draw, as I told you, we can draw anything you like, but because we mainly interested in we have drawn some electrodes or bios. This is a key terminal electrochemical cell in here. So this is working electrode, this is counter electrode, and this is reference electrode, all made by that. And these are, and we also could draw the connecting parts as well. And this is a multiplex. So when you look at these electrodes, you see 1, 2, 3, 4, 5 electrodes, working electrodes, all are in connection with one universal counter and one universal reference. This, for instance, allows us to measure different active materials in an analyte. We also can make supercapacitors, for instance, and with any type of geometry that we like. For instance, this is the classical level type supercapacitor, and then we apply it to make mains type supercapacitor as well. So these are all in progress type of applications. They are all in progress right now with the students that you saw at the beginning. And if we want to have a closer look at that graphene you have, so there's a polyamide surface here. It's extremely smooth. There's the laser converter graphene. Now that looks a little bit different, right? So this is a formula, extremely porous film. And the thickness of that film is around 30 microns. When you look even a little bit closer, you see that we do have a good sheet, sort of like thickness, a few nanometers of thickness, which also tells us like a few layers of graphene that are located. This is it. So this was an extremely sort of like nice to get. And the beauty of it, it doesn't change from one fabrication to another. Okay, so you make your graphene film, you take it to SEM, and whenever you take it, you get the same exact porous structure with similar porous size, pore size, and everything. But it's a little bit tricky with graphene, to be honest. But with this technique, it's extremely repeatable. When we look at the XPS results, X-ray photon spectroscopy, we, of course, first performed a survey spectrum to see what we have on the surface. Because if you remember, we do have nitrogen contents in polymer. But after the conversion, we lost that nitrogen. There's no nitrogen. We do have oxygen, we do have carbon. These oxygens, they correspond to defects of graphite, which are located at the sites, and they are usually carbonyl units or hydroxy units. Okay. And when we look at the XPS survey, we see that this material is dominated mainly by carbon, NSP2 carbon, which presented itself at 286 electron volts. And after that, few amounts of oxygen presented themselves at 534 electron volts. Let's have a closer look at that beautiful carbon that we have. So this is the closer look, focused version of that document. And when we fill it with dosimetry, we get simply carbon double bonds at 285, single bond carbons and carbon hydrogen bonds at 287, and also the carbon double bond oxygen, which presented itself at 289. These are all in agreement with the literature in terms of graphene with defects. Is it bad to have defects in graphene? Is it bad to have oxygen groups? Are we the extremely perfectionists? Actually, we don't want perfect graphene, my dear friends. You wouldn't want the perfect graphene. Perfect graphene, that perfect single layer graphene is extremely hydrophobic. You cannot use it in any application. Okay, but if it has a negligible small amount of oxygen entities, it suddenly becomes a little bit hydrophilic. It loves water. It loves electrolytes. It works with that. And then suddenly you get beautiful charge transfer reactions, especially if you use it in lithium-ion batteries or biosensors, etc. Okay? Single layer perfect graphene is okay, is beautiful if you are using it for solid state applications. If you are using anything involves any graphene, then you actually need these defects that we have in here. And after the XPS, we also performed some XRD experiments, which gave us a very intense peak centered at 26.10 to theta, which indicates a high level of graphenization with multiple layers. So this was also what we expected, because from SEM pictures, we know that we don't have single layer, we have few layers, we have a lot of layers, right? So that's good. Our XRD data also confirmed what we have. Also, that small peak that we see here at 43.1, that indicates the planar structure of the graphene, which is what sort of, which indicates that we have graphene with multiple layers. This confirms exactly what we saw in SEM figurines. We also checked FTIR. So this was nice, okay? So when we looked at the FTIR of polyamide, you see, because of all that functional groups, you have ridiculous amount of peaks. Each indicates different sort of modes for carbon, carbon, carbon, hydrogen, carbon, oxygen, carbon, nitrogen bonds, which I'm not going to get into that, because what we are interested in is using nothing. Or most of the functional groups are, this is what we were looking for. So that was a quite nice sort of measurement that we like. And we know that we can make films, and we know that we can make them in any pattern we wish. That's okay. And we were like, can we also get powder to make composites? And it turns out we can. First, we laser scribe our polyamide in a sort of bigger, because this is what we can, right? We scribe it in a big rectangular or square form, doesn't matter. And then we're using a stainless steel plate. We actually scribe it from the surface, and we can collect it onto, we can collect it in sort of high scale, in big scales. We are talking about grams in here. And if you don't do anything, if you just scribe it, of course you will have some big chunks as well as small ones, right? Currently, we are working on how to make these big chunks smaller. And the first thing that we tried was simple mechanical grinding, okay? And that worked beautifully. Even that one brought down to the flakes to around 2 micron in wide. So that's really good, because we still have a thickness of few nanometers. Now we have it this way, and then our further experimentation will be based on making it smaller and smaller to make it nanoflakes that can be used for different applications. But even this can be used for making composites. So no problem, we are currently making composites. In terms of conclusions, so we can make our graphene either in film or powder form in a computer controlled way that we can draw any pattern. It's a green synthesis. Did you see? No chemical involved, nothing. So it's beautiful. It's time efficient. It is produced within milliseconds. Those electrodes that you saw, each of them cost around 1 minute to make. Even a whole A4 size can be made in within minutes, no problem. It's cost effective. So all we need is a polyamide film and suitable for scaling up. We already scaled it up. So it is good. What we are going to do with this is a recent, by the way, this is a recent study. I have been recently appointed, my students and assistants recently started. So this is all a story of 3 months, really. So that's why I was saying I'm very lucky to have such amazing students. In future, we will build field effect transistors, integrated circuits, interdigited electrodes. We already made interdigited electrodes. You saw the pictures. That leather design is called as interdigited electrode. And we will use them for biosensing, chemosensing, pressure sensing, and supercapacitors. Also, with using powder, we will develop composites to make flexible electronics, flexible solar panels, and artificial muscles. I did a little bit work on artificial muscles during my PhD. It was a side project. We published a few papers, but I still have my mind on it. It's such a beautiful project. So my group will also continue in that as well. And thank you all for listening. And any questions, please. Yes. I don't know. We can try. This meeting is taking place. That should be actually a slow. Okay, that's nice. Çok ilginç bir şey var gerçekten. Bunu düşünmediler mi kimse daha önce bak. Yani çok ilginç bir şey çıkarttık. Ya bunu düşünelim. Konuşalım yani. O zaman ben çok önemli. This particular, this language is not good. I'm not signing things we made from chilies, but we have to extract the review. We can make the secret lasers, but what you
O zaman siyah olmanı zaten I don't know. Any questions from the online participants? I don't know how you can see that.
Hocam online'da soru gözükmüyor şu an.
Gözükmüyor. Okay. Good.
Evet.
Maybe one small question. Have you measured the electrical conductivity?
Yes, we did. 1,100 Siemens per meter, Siemens per meter. Really high. Almost metallic.
I think we should thank one more time the speaker and I should present the participation.
Thank you very much. Fotoğraf çekin. Bir fotoğraf çekin.
Tamam. The speaker is now a Master of Science in engineering program. His main research is on environment for air acoustics stations. And now he is moving
Evet. Yapıntı takmak için. Şu an
Geldi hocam görüntü.
hocam tam ekran mı?
Şu an gitti ama tekrar.
Evet. Tekrar açıyorum. Şu an tam ekran gözüküyor mu?
Bir dakika. Şu an gelmedi bana.
Ben bu şekilde
Görüntü yok şu an.
gönderiyorum hemen. O da yapıyor aynı şey.
Tamam. Şu an geldi hocam. Tam ekran.
Şu an değişim yok ama. Slide'lerde olan yanlış şeye tıkladığım için oldu. Şöyle. Geçeceğim. Sonlandır bir daha. Ve kapayıp sonlandırdım şu anda. Böyle
Şu an geldi. Büyütebilir misin Yasin hocam?
Sen görebiliyor musun hocam?
Evet şu an iyi.
Tam ekran mıdır?
Tam ekran. Değil. Şu an değil hocam.
Değil mi?
Değil.
Yanda notları mı görüyorsun?
Aynen.
Ya şurada yeni paylaşımları alırsanız. Anlatayım şimdi. Yeni paylaşımları. İkinci ekran. Şu an
Şu an tam ekran. Tamam
Şu
şu
an-
an. Evet evet hocam tam ekran.
Hello and good evening, everyone. Today I'll be sharing my research or my experiments that was done at Timur Labs under the supervision of Dr. Ali Kılıç with my colleague Melike. The title of our research was on TPU-based nanofibrous membranes and their potential use as a battery separators or lithium-ion battery separators to be specific. Firstly, to understand what are battery separators are fibrous or membrane structure, not exactly fibrous, but a porous structure that separate our electrodes, the anode and cathode, prohibiting any contact between them. And by that, it prohibits any kind of short circuits that could happen. Mainly, this porous structure should be ionically conductive and electrically insulated, while it should provide minimal resistance for the ion movement from the anode between the anode and cathode. Also, it should show a high mechanical and thermal stability with high porosity. It can be either polymer blends, composites, nonwovens, or it could be nanofibrous or from nanofibers. And that's what we have done. We have made them from nanofibers. as we all know, nanofibers are one-dimensional nanostructures or nanomaterials below the 1,000 nanometer range. They are known to be lightweight with controllable pore structure. They have a high surface to volume ratio, making them applicable in many sectors like batteries or filtrations, either water or air filtration. To obtain nanofibers, there are many fabrication techniques. We have the most common or most familiar one, which is the electrospinning technique, where they utilize the potential difference or voltage to obtain the nanofibers. Also, we have air jet spinning, where we utilize the air or pressurized air to obtain the nanofibers from polymer solutions. Lastly, we have centrifugal spinning, which is the one that we have used in our research. In centrifugal spinning, we mainly use a motor-rotated nozzle that spin at very high speeds, up to 15,000 RPM, ejecting the fibers and evaporating the solution of the polymer solution, and obtaining finally the nanofiber. It's known to be, it has a lower cost in comparison to electrospinning. So in our experiments, we have used TPU as the base polymer for our nanofibers. TPU, the grade that we have used is ester-based, and it's known to have a higher mechanical and better chemical stability in comparison to other TPU grades, which is the ether-based. It has a high elasticity, high abrasion resistance. It's known also to be biodegradable, which means that it's recyclable. And we have used sodium alginate to coat our nanofibers. Because sodium alginate, firstly, it's a natural polymer. And the main reason that we have used sodium alginate is its inherent flame retardant whenever it's cross-linked with divalent ions like calcium, magnesium, or barium. And also it's non-toxic. And at the same time, because TPU is hydrophobic, the grade that we have used is hydrophobic, we have used sodium alginate to modify the surface properties of our fibers and making them hydrophilic. I've said that we have used sodium alginate mainly for the flame retardant property, and it's very important in batteries, because in battery, whenever it's exposed to elevated temperature, our membrane got melted. Whenever it's melted, we have the electrodes come in contact with each other, causing a short circuit. Whenever a short circuit is happening, that means that temperature would increase more. And whenever it's increasing more, that means that more volatile component, more combustible gases are being released, which eventually lead to an explosion. Our experimental scheme, firstly, we started with optimizing the process to achieve the best fiber diameter. Spinning it at centrifugal spinning, obtaining the nanofiber, then dipping it in sodium alginate, waiting it to dry. Then after that, we cross-linked it with the calcium chloride. Finally, we have hot pressed our samples to obtain a better mechanical stability. And eventually, we sent our samples to characterization with different methods, with different devices. Coming to our results, firstly, we have based on the literature, we started our parameters with the 23 gauge needle diameters, 80,000 RPM, and 3:1 DMF acetone ratio. From there, we have obtained the best. We changed the concentration with these constant parameters. We have used 5, 10, and 15% concentrations, and we have seen that the best fibers were obtained in 10% with to be honest, with a negligible amount of beads. After that, we started changing the solvent ratio, and we observed that whenever we are increasing the acetone ratio, we were getting rid of the beads, but in the same time, in the expense of increasing our fiber diameters. So we found that 2:1 gave us the best fiber diameter with the minimal amount of beads. After that, we have changed the needle diameter to between 23, 25, and 30 gauge to get rid of the beads that were forming on the expense of a very slight increase in fiber diameters. After that, we have changed our rotational speed. We have increased the rotational speed from 8,000 RPM to 15,000 RPM to obtain a final, very small fiber diameters in the range of about 300 nanometers. And the final, these are the final parameters that we have used in the rest of our experiments, which are 30 gauge needle, 13,000 RPM, 2:1 solvent ratio, and all of 10% TPU concentration. After that, we coated our samples with 0.5 and 2% sodium alginate. And we've seen that whenever we are coating it with 0.5, anything above 0.5 sodium alginate concentration, we were losing the fibrous structure of our membranes. Yet in 0.5, we have to some degree maintained our fibrous structure with an acceptable amount of porosity. After sending them to hot press application, whenever we are pressing our samples or our nanofiber membranes, we were fusing the interfiber contact points, making them having high stiffness, which is better for our mechanical performance of our separators. We have done it at for 2 minutes at 120 degrees Celsius for under 8 tons of load. Finally, we have examined the contact angle. We can see that our neat non-pressed TPU showed a 107 degrees, but whenever it was coated with sodium alginate, we dropped the contact angle to about 31, and which after like 5 minutes, it would completely be soaked in our samples. For the dimensional thermal stability, we have exposed our samples. We have put our samples in an oven for 2 hours at 200 degrees Celsius and examined the shrinkage of our samples. We can see that our neat TPU sample got shrink by 63%, which is devastating in any battery performance. But for 0.5 and 2% sodium alginate, we have obtained almost less than 5%, which is in the ideal separator specifications. And comparison to the commercial one, which is polypropylene based, of course, it was completely demolished. After that, we have done our flammability tests. We can see that it's not working. Okay. To be honest, unfortunately, it's not working. I'll be explaining it. The neat TPU, whenever it was exposed to the flame, it got shrink and the polymer started dripping. But whenever it was coating, it was getting burned without any shrinkage, just a formation of a char layer that it turns into black. The sample turns into black without any without catching the flames. So whenever it catches the flames, it totally suppress the flame and extinguish it. It would be better if we have seen the videos, but it's not working. So the mechanism there that happens, sodium alginate or calcium alginate, there are mainly it follows mainly two pathways in the formation of the volatile compounds. The first one is it forms the purfural. This one makes the char layer. The char layer become like a barrier between the TPU nanofiber and the flame, and this barrier would just suppress any flame, any advancement of the flame, while the butadiene forms a gas that is non-combustible, which dilutes the concentration of the combustible gases. So by that, it would also suppress the flame formulation. Finally, we have send our samples to the EIS or chemical impedance spectroscopy to measure their ionic resistivity and their overall ionic performance. And we have found that the 0.5 calcium alginate treated TPU samples performed better than either mid TPU or the 2% calcium alginate samples by 0.2 millisiemens per centimeter. Finally, we have the future studies that we are planning to make on either the mechanical integrity, chemical stability tests, of course, the cyclability of our samples, and enhancement their porosity. I would like to thank BAP grants for their financial support for our study, Arica Advanced Technologies for their machinery, and Timag Lab, of course, by providing the accessibility to the facilities. Thank you for listening, and I'll be happy to accept any questions.
You know the difference of elaborating all over. Any questions from the online audiences? In case.
Online sorunuz var mı hocam?
Soru var mı orada?
Online'da soru yok hocam.
I'm gonna ask. I'm just separate base analysis is device. Base electrochemistry methods has which one is the best? What is one?
Yeah. Alginate coated one, which is in the middle, it's better than the one in the left, which is the nitty. So it's perfect. Yes. We haven't done the full cell tests yet, but we are planning to do them. Yeah, from the resistivity, we are measuring the ionic conductivity, yes. Yeah, but mainly to judge on the overall performance of the separator, we need to make a full cell, anode, cathode, and the separator in the middle, yes.
And certification is more on your end. That's all.
Açayım mı böyle? Açabilirsin. Ancak şunu kapatabilir isterseniz.
From chemistry department, and then she has done PhD at Composites. Very interesting because
İlerliyor hocam, bir sıkıntı yok şu an.
global project in chemistry,
Yes.
and you work.
Görüntüm yok dediniz.
So that she joined a project, I think, Holland, right?
Yeah, 1,000, yes.
The UP project, postdoc study over there. Now she does actually excel department and she postdoc and she will talk on this issue, probably this issue of GMP components.
Thank you. Good afternoon, everyone. In my main expertise area is, in fact, nanofibers in biomedical applications, but my current project is based on the use of graphene nanoflagellates for improved thermal conductivity. So it is a new area for me also. The presentation will include basic information on nanofibers and electrospinning, thermal conductivity, aim of the study, results, and some conclusions and future work. Firstly, of course, I will start with a brief information on nanofibers. As the previous speaker also explained, nanofibers are materials with diameters below 1,000 nanometers, but usually 500 nanometers in the literature. They have high specific surface area, small pore sizes, and high porosities. And in this image, you can see a simple human hair and some nanofibers to give you an idea about how thin these materials are. The most widely used technique to produce nanofibers is electrospinning. It is a simple and low-cost method based on the use of voltage. In this technique, the main components are a pump for feeding and a power supply and a collector. The polymer is either melted or dissolved in a solution and placed in a needle, in a syringe connected to a needle, and it is fed with a constant flow rate using a pump. And the solution comes to the tip of the needle in a spherical shape, and as we apply some voltage to this droplet, a conical shape occurs because the droplet is held there with some surface tension. And when we apply a voltage overcoming this tension, the droplet becomes a conical. This is called tler cone, and it is one of the basics of electrospinning. And a jet is ejected from the tip of this tler cone, and with whipping motion, it is collected on the grounded collector. And of course, this process is based on many parameters, like process parameters. It's like the flow rate and applied voltage to the collector distance, and some solution parameters like the concentration and the solvent use, polymer type, and ambient parameters such as relative humidity and temperature. Using this method, we can produce various types of materials, from beads to nanofibers and hollow nanofibers and to porous structures. And the unique properties of these nanofibers make them valuable for many application areas, such as filtration, composites, sensors, technical textiles, and biomedical applications. It is most widely item used for biomedical applications because these nanofibers resemble to the structure of the extracellular matrix. It is also a fibrillary structure. So in the literature, you can especially find many applications based on like wound healing or immobilization, tissue engineering, immobilization of enzymes, etc. And I will shortly also talk on the conductivity-based properties. The heat dissipation route of human body includes 4 basic routes. These include the conduction, convection, radiation, and evaporation. And the main role of a clothing is also to provide the thermal balance between the human body and the environment. And if the skin temperature is higher than the surrounding, then the clothing should insulate the body and to prevent the loss of body heat through conduction, convection, or radiation. And if the skin temperature is lower than the surrounding, then the human body can gain external heat by conduction, convection, and radiation, and can get rid of the excess of the heat by evaporation. Conventional textile materials and also polymers usually have a low thermal conductivity, and the reason for the low thermal conductivity in polymers basically depends on the morphology of the polymers, because usually polymers contain amorphous domains and crystalline domains, and if the amorphous domains are the dominant one, then the thermal conductivity becomes lower because the vibrational modes tend to localize. Here you see the conduction mechanism in an ideal crystal structure and in amorphous polymers. In ideal crystal structure, when an atom absorbs heat, it can vibrate in a frequency and then transfer heat to the adjacent atom with the same frequency. But in polymer composites, phonon scattering can occur, and this results in low thermal conductivity. And so one should improve the chain alignment in polymers to improve the thermal conductivity. And this is usually done via mechanical stretching, nanoscale templating, and electrospinning in literature. And another way to improve the thermal conductivity of the polymers is to add conductive fillers in these materials. If conductive fillers are added at a sufficient amount to the polymer surfaces, we can and conductive network can occur within the system, so we can improve the thermal conductivity of the composites. And these are the examples used mainly in the literature for improving the thermal conductivity, including graphene, carbon nanotubes, boron nitride nanotubes, or some phase change materials. And the main aim of this study is to use a recycled polyester and to add some value to this recycled polyester, because recycled polyester is usually used to make low profit applications, but we aim to provide we aim to add some value to this recycled material, so we can contribute to both to the environment and to economy. And we try to produce a reinforcement layer by making some polyester, graphene nanoplatelet, composite nanofibers, and we aim to distribute the heat in the body evenly, for example, from a hotter place of the body to a lower temperature place of the body by using this thermally improved nanofibers layer. For the preparation of these nanofibers, we first dissolve recycled PET pellets in a solvent system composed of dichloromethane and trifluoroacetic acid. We magnetically stir them until we have a homogeneous solution, and then we add the graphene nanoplatelets in this solution, and we make a homogeneous dispersion using ultrasonication and magnetically stirring, and then electrospin this dispersion. I made some preliminary experiments to find the optimum conditions for recycled PET electrospinning, and I found the conditions as 15% of PET solution in trifluoroacetic acid dichloromethane solvent system using 20 kilowatts as the applied voltage, 1 milliliter per hour as the flow rate, and 20 centimeters as the tip collector distance. So I use these conditions for both the reflect nanofibers and composite nanofibers. And here in the SEM images, we can see that the average diameter for the recycled PET nanofibers was around 271 nanometer, while it increased to around 500 nanometers with like 10% graphene incorporation in the solvent solution. And here you can see it both in the SEM images and TEM images that graphene distribution is visible in the nanofibers, and in some parts there are agglomerations of the graphene nanoplatelets. In the FTIR spectrum, there is no very apparent difference between PET nanofibers and composite nanofibers, because the graphene doesn't give a very obvious peak. In the infrared region, we can see the basic characteristics bands of the recycled polyester, like the carbonyl units. In the Raman spectrum of composite nanofibers, we can see the characteristic DG and 2D bands. The G bands at 1573 shows the sp2 heat hybridization of the graphene, and the D band shows the disordered structure in the graphene, while from the 2D band we can see that this is a multi-layer graphene. Biraz takılıyor. Bir daha basayım. Burada takar. Then we investigate XRD patterns of the PET and composite nanofibers. In PET, there is an amorphous hollow of the polyester at 2 theta 19 degrees. And in the composite nanofibers, we can see the 002 crystal lattice of graphene nanoplate at 2 theta around 26.6 degrees. And also when we investigated the average water contact angles of these nanofibers, I observed that the average contact angle of the composite nanofibers was decreased nearly 30 degrees. Then I investigated thermal properties of these nanofibers. From the DSC, the melting point of the composite nanofibers was not affected, but the crystallization temperature was increased with the incorporation of graphene nanoplatelets, and this can be due to the pronounced nucleation with graphene incorporation. And in the thermal gravimetric analysis, I saw an early degradation of the composites, and this can be due to agglomeration, I guess. And the repeat composition occurred between 310 to 500 degrees. And the end temperature of the composite nanofibers was around 530 degrees. And if you look at the residue of repeat nanofibers was around 10%, while it increased to 32% for the composite nanofibers. So we can say that they became more thermally stable. Lastly, I investigated the thermal imaging of these nanofibers by placing these nanofiber surfaces on a heater, and I took thermal images during heating from room temperature to 60 degrees, and we can say that the heat dissipation of the composite nanofibers became more faster and evenly when compared to polyester nanofibers. And we had a thermal conductivity test on these fibers using the laser flash method, which measures the in-plane thermal conductivity of the materials. And it was around 12 watts per meter Kelvin for the PET nanofibers, while it increased to 25 watts meter Kelvin for composite nanofibers. And as a conclusion, we successfully prepared polyester and polyester graphene containing nanofibers, and we investigated them morphologically, spectrally, and thermally. And as the future work, I will perform some mechanical testing as well as air permeability and washability testing, as these will be used for textile reinforcement layers. So thank you for listening.
Just wondering how the conversion test this stage
No, actually, I did some preliminary washing test, and it stays. Yes, I made 5 washing tests, and it stays. But I mean, I didn't do any experiments on these washed ones, but it didn't go away.
Graphene are already embedded in the fiber. That's why.
Yeah. I mean,
It's already inside.
yeah, they are not on the surface. It's also in them. So yes, they stayed.
That means we use modification clothes for we wear. It's not unhealthy. Just didn't release. I can use the kind of thermal clothes. Let's say for some water,
Yes.
I mean, and it's not unhealthy.
Yes. Graphene itself, I think, also antibacterial. I believe.
Both diet and so also harm the plants. That's why they say take the precaution, don't inhale the graphene, make problem. Thank you.
This is from the online.
Do we have any question, comments? No? No. So we will thank you very much for time participation in that and yes. Belki soru sormuyorsun yani.
Shall I start now?
Not yet. Yeah, we will tell you. Hocam, diğer sınav 10 mu? 10 ya. Do you hear us?
Sure, I hear you.
Good, very good. Welcome to our session.
Thank you very much.
Just give us a second, okay?
Okay, I'll wait.
Next speaker will be from Addis Ababa, Andinet Kumele Eticha. He is a PhD student at Karabük University. He graduated with Bachelor of Science in 2011 and Master of Science degree in 2014 from Addis Ababa Institute of Technology. Now he is Addis Ababa University from Mechanical Engineering Department. Currently, he is working on biodegradable nanofibers for air filtration, and in his PhD study since 2012. Please, Andinet Kumele, you could start with your presentation.
Okay, you can share your presentation.
Is it visible?
No.
Not yet.
About now?
Yes, we see that now. Please make it in the presentation form.
Okay.
You can start.
Okay, my name is Andinet Kumele, and I'm from Karabük University. And first of all, I would like to thank all of the researchers who have participated in this research work. So before I go directly to my presentation, I will start by saying good evening. So our title is majorly focused on electrical assisted solution blowing of PVDF rosemary nanofibrous webs for food packaging applications. So I will start my presentation from the introduction, and I will go step by step until the conclusion, actually. So we are applying this packaging technology for the foods. Actually, this active packaging system is a new technology, which is very different from the traditional one, in a sense that the packaging, this active packaging, not only extending the shelf life of the foods, but as well as protecting the consumers from a possible risk of pathogens. While doing this one, this active food packaging or a material to be used as an active food packaging, it should have to fulfill 4 basic criteria. The first one is hydrophobicity. It should have to be barrier from moisture, and there is an antioxidant. The material should have good mechanical strengths, and there is an antimicrobial characteristics, which helps for inhibiting the possible microorganisms actually. So for this active food packaging system, nowadays these nanofibers are hugely applied because of their production methods that give us a high surface area to volume ratio and with their high porosity. And also that in order to meet the above listed criteria, these nanofibers can easily modify their character by maybe blending with some chemicals. We can get some improvement in the mechanical strengths. We can also change the hydrophobicity using heat treatment, which is a physical means. We can also use ultraviolet rays. And the other is, for example, if the nanofiber to have antimicrobial activity, we are going to use some active agents like essential oils in order to prevent it from the possible development of microbes near the foods actually. So these nanofibers, which are applied for food packaging, basically they are made from either natural or synthetic polymers type. But these bio-based polymers, if the nanofiber is made from these bio-based polymers, it have its own advantages and disadvantages. So the biodegradability, environmental friendly, these are the possible major advantages that a nanofiber obtained from bio-based polymers. But their short molecular chain lengths makes them difficult while we are trying to produce them actually. And there is also, apart from the ketosane, there is a poor bioactivity were seen for these bio-based nanofibers. Their mechanical properties also low. So for instance, if we look at our past research studies, for example, for gelatin-based nanofiber and PVDF and PVP-based nanofiber, as you can see here, there is a huge difference in terms of their mechanical strengths. Because mechanical strengths, we need the elasticity tendency for the food packaging system. So when we focus our focus on this PVDF-based nanofiber, because our research mainly focus on that, it is mechanical strength, as you can see, it is very high. It has good thermal stability. The chemical resistance is also high. It is non-toxic, which is very crucial for the packaging industry. But it has low antimicrobial property. So in order to improve its antimicrobial property, we try to use some active agents like metals, ketones, essential oils, lysosomes, and lactoferrin, which are antibacterial property. Among these metals, the silvers, copper, and its alloys have some antibacterial effect against Escherichia coli and Staphylococcus aureus. Ketosane by itself, it has an antibacterial property, but essential oil, as can be observed from the literature survey, they have a vast application in terms of antibacterial, antioxidant, and antifungal characteristics. Because of that reason, we select these essential oils, particularly rosemary essential oil for the food industry in order to blend it with the PVDF. So this is our objective. So we are going to blend this rosemary essential oil toward the PVDF using electrically assisted solution blowing technique. We use this technique sometimes. This is a blend of electrical spinning and solution blowing technique. So sometimes in order to get the best advantage out of two systems, systems can be hybridized. So we are blending it. So the nanofiber that is produced will have a high aspect ratio. During our preparation, the PVDF solution is prepared using a mixture of DMF, which is a lignization for dimethyl fluoride and acetone in the weight ratio of 7:3, and stirred at 40 degrees Celsius for 12 hours to obtain a 12 weight% PVDF. Once the PVDF solution was prepared, 3 different rosemary essential oil concentration in the form of 1, 5, and 10 were added, and then it stirred 1 hour at room temperature. So once this solution is ready and it's put into this electrically assisted solution blowing, so with the defined solution and process parameter. And this is the nanofiber that we produced using PVD, 10 weight% of rosemary essential oil with PVDFs. This is for a sample. So our characterization is for the packaging. We try to characterize using a scanning electron microscope. We are going to use this gas chromatography for identifying the individual constituents. And we are also tested the antimicrobial activity. So when we come to our morphological analysis, based on the morphology and the fiber diameter distribution, here, as the orange color indicates, increasing the oil concentration tremendously improves the fiber diameter. Therefore, pure PVDF has a relatively lower fiber diameter as compared to higher concentration included PVDF solution. And the other is, and this increment in the increment in this nanofiber diameter can directly link with the viscosity of that solution, which is increased because of the addition of the oil. And when we come to its morphological appearance, as you can see here, apart from this 10% rosemary essential oil, the others, there are beads and droplets were embedded in them. So relatively, a smooth bead, droplet-free nanofiber morphology was observed in the higher rosemary essential oil concentration. So from this, we can say that the oils can easily segregate inside the nanofiber, which enable us to the nanofiber to release that oil so that it can protect the nanofiber from, the food from the pathogens. And while considering this, the GC, or it is a tool which is used for identifying the major constituents in the rosemary essential oil. Basically, here we use 2 phases, which is the mobile phase and the stationary phase. And this mobile phase is an inert gas, which can be helium or argon, which is going to drive through the sample in a column. So when the constituent, this rosemary essential oil is in vapor form, so the constituent with low affinity will have a lower attraction towards the stationary phase. So it can move freely in a quick manner. However, with a constituent or analyte with a higher affinity, it has greater interaction with the stationary phase so that its movement will be lower. So this is the principle behind this gas chromatography for identifying the major constituents which forms the rosemary essential oil sample. So based on the identified here, a total of 9 major constituents were identified. Among these, this camphor, alpha-pinene, and 1,8-cineol are the major constituents that determine the characteristics, which is the antibacterial and antifungal characteristic nature of this rosemary essential oil. And when we go to the antimicrobial test, based on the disk diffusion. The antimicrobial zone diameter, as can be observed, is increased with according to the increment in the concentration of oil. So as you can see here for Escherichia coli bacteria, the diameter, which is the zone of the sample, which is inhibition, which is free from the bacteria, is much higher and nearly 4 millimeter in diameter. And also for Staphylococcus aureus is similar case. And for 5 and 10%, we observed that the antibacterial and the antimicrobial, the antibacterial and the antifungal effect was hugely or significantly observed. In conclusion, the addition of the rosemary essential oil improves the nanofiber diameter, and the major constituents of the rosemary essential oil, which gives the antimicrobial effect on the nanofiber, are the camphor, alpha-pinene, and this one. And finally, from this study, what we observed based on our characterization on based on our characterization, we determined that this PVDF rosemary essential oil have huge potential to be applied for antimicrobial active food packaging. Thank you very much for your attention.
Thank you very much. Questions? Now, we should thank you one more time on the you would receive your participation date, and then you come to or we can send you online, okay, by email.
Thank you, thank you.
Yeah, we have an online certification for the. Thank you very much.
Thank you very much.
We have one was speaker, Dr. Bungi Hanım, from third of India. India is one of our speakers of our conference. Please go ahead.
Değerli akademisyenler, sayın dinleyiciler, hepiniz öncelikle hoş geldiniz. Kısaca size kendimden bahsedeyim. 2009 yılında Hacettepe Kimya mezunuyum. Ardından Uludağ Üniversitesi Organik Kimya bölümünde bir TÜBİTAK projemle birlikte yüksek lisans eğitimimi tamamladım. Hemen arkasından yine aynı üniversitede bir TÜBİTAK projesiyle doktora eğitimimi tamamladım. Paralelinde bir doktor öner firmasında 10 yıl Ar-Ge'de çalıştıktan sonra MBA'mi gerçekleştirerek Sözel Kimya'da 5 aydır Ar-Ge Merkezi Müdürlüğü'nü üstlenmiş durumdayım. Ben açıkçası da şu an çok duygusalım çünkü yıllardır her sene düzenli olarak katıldığım bir kongrede bu sefer sponsor olarak yer almanın heyecanı içerisindeyim. Ve size kısaca Ar-Ge Merkezi tanıtımımızı gerçekleştirmek istiyorum. Sözel 2007 yılında sadece 5 kişilik bir ekiple 150 metrekare alanda kurulan bir firmadır. 2 sene sonra ise Kestel bölgesinde laboratuvar ve depo yatırımı yapmıştır. 2013 yılında ise şu an halen bulunduğumuz tekstil kimyasalları ve boya bölümlerini içeren yaklaşık 10.000 metrekarenin üzerinde bir alana sahip bir şekilde yerini almıştır. 2016 yılında ise yine Sözel Kimya Ar-Ge Merkezi bünyesinde bulunan plastik bölümünü 35.000 metrekarelik bir alan üzerine yatırım yaparak gerçekleştirmiştir. Ar-Ge Merkezi ünvanını 2017 yılında aldık. Ve Ar-Ge merkezi kapsamında son dönemde yaptığımız 3 adet TÜBİTAK projemiz, 1 adet patentimiz ve 1 adet faydalı modelimiz bulunmaktadır. Söz alışı size şöyle anlatabilirim aslında. 2 farklı lokasyonda tekstil kimyasalları, plastik master batch dediğimiz ve boya dediğimiz 3 farklı alandan oluşmakta. Bugün en güçlü olduğumuz yönümüz aslında tekstil boyaları. Çünkü boyalarda aslında dünya markası bir Colortex'le çalışıyoruz. Ve buradaki mevcut potansiyelimizi aynı şekilde tekstil kimyasallarını taşımak bugün en büyük hayalimiz. Yine bu kapsamda plastik kısmımızda ise gerek yaptığımız yatırımlar, gerek Composites vermeye çalıştığımız yeni hizmetlerle büyüme yolculuğu içerisindeyiz. İhracat yaptığımız ülkelerin başında Bangladeş, Rusya, Özbekistan ve Türkmenistan gelmekle birlikte dünyada 25 ülkeden fazla bölgeye ihracat yapmaktayız. Türkiye yapılanmamızda ise Trakya bölgesi, Ege, Güneydoğu Anadolu ve Orta Anadolu, Marmara bölgesi olmak üzere hem depomuz hem satış yetkililerimiz ofislerde bulunmakta. Üretimimiz tekstil kimyasallarında ortalama 72 bin ton olup, plastik kısmında ise yıllık 18 bin ton civarındadır. Üretimlerimizi yaparken ilk önceliğimiz reaktörlerimizin ex-proof olması. Biliyorsunuz son dönemde çıkan yangınlar hepimizi çok üzmekte ve bu alanda Sözal gerçekten çok önemseyen bir firma. Ve ham maddelerin alınışından tutun da son sevkiyatına kadar bu konuda özellikle müşterilere servis verirken dikkat etmekte. Ar-Ge faaliyetlerine gelecek olursam, 23 kişilik bir ekibimiz var. Az önce size bahsettiğim gibi Ar-Ge merkezi bünyesinde zaten patentlerimiz, TÜBİTAK projelerimiz mevcut olmakla birlikte belki 20'den fazla in-house dediğimiz projelerimiz bünyemizde bulunmakta. Ar-Ge ve Ürge ekibi çalışanlarımızın neredeyse yarısı ya yüksek lisans doktoralıdır ya da yüksek lisans doktora öğrencileri şu anda ve birçoğu TÜBİTAK projeleriyle bu çalışmalarını yürütmekte. Laboratuvarda uygulanan testlere bakacak olursak, müşterilerimiz biz sadece ürün alsat ticaret şeklinde bakmıyoruz ve bize çok fazla aslında testler gönderiyorlar. Bu kapsamda onlara en büyük hizmeti verebilmek adına sürekli test cihazlarımızı ve makinelerimizi yeniliyoruz ve ekranda gördüğünüz testler bizim en rutin olarak yaptığımız, bu konuda ciddi bölge uzmanları ile birlikte gerçekleştirdiğimiz testlerimizdir. Ürün gruplarına gelecek olursak, az önce de aslında bahsettiğim gibi kimyasal, boya ve plastik olarak sınıflandırabiliriz. Kimyasal kısmında ise ön işlem, boya yardımcıları, apre kimyasalları, teknik tekstiller, haşıl ve baskı kimyasalları adı altında gruplandırılmaktadır. Tabii bunların hepsinin altında alt gruplarda mevcut. İlgilenenler olursa zaten yarın da buradayız. Bir masamız var. Orada size ürünlerimiz hakkında daha detaylı bilgi de verebiliriz. Boya bölümümüzde ise reaktif, dispers, naylon, mat, baskı boyalarımız mevcuttur. Plastik kısmında ağırlıklı olarak siyah, beyaz, renkli ve katkılı master batch'ler yapmaktayız. Ve biraz önce de söylediğim Compound'a gerçekten bu sene çok büyük yatırım yaptık ve ilerleyen dönemlerde plastiği aslında master batch ve compound olarak birlikte yürütmeyi düşünüyoruz. İlginize çok teşekkür ederim. Çok sağ olun.
This is the story for today. Hopefully, you're going to meet more.
Kapatabiliriz. Oturumumuz bitmiştir burada. İyi günler arkadaşlar. Oturumumuz bitmiştir. Görüşmek üzere. Yarın sabah tekrardan başlamak üzere. Görüşmek üzere.
Hocam bir fotoğraf çekilebilir mi?
Hocam kapatıyorum.